Hello friends and welcome to another lecture on chemical engineering thermodynamics. Today we'll be taking a question from Mumbai University December 19th paper. The question is question 4A. This has come in CET 1 Chemical Engineering Thermodynamics 1 paper. The question is on your screen. You have to estimate the fugacity coefficient of N-hexane at 600 Kelvin, 800 kilopascals using van der Waals equation of state. Now, you do not have to mug up the formula and come. It can be simply solved using very fundamental equations of fugacity and the calculator. So please do not mug up the formula. Just pay attention to how I solve it and get the answers. Okay. So we all know that dg is equal to RT into d ln of F for a real gas, where F is the fugacity. And also it should be noted that dg is equal to V dP. And for an ideal gas, it is dg ideal gas is equal to RT into d ln of P. So it goes without saying that for an ideal gas, the fugacity is equal to the pressure. Now, if we subtract equation 1 and equation 2, we end up getting dg minus g ideal gas over RT d is equal to d ln F by P, which is nothing but d ln of phi, where phi is the fugacity coefficient. Now, we need to understand here what we are interested in is calculating the fugacity coefficient. So what we have now is d ln of phi is equal to 1 over RT and dg minus dg ideal gas. That's simply 1 over RT V dP minus V ideal gas dP. Take a note of this equation. Okay, so what we have now is 1 over RT V minus V ideal gas dP. Well, this is a compact equation, of course, but this compact equation is something it can't be of much use to us. We have to modify the last equation. So remember 1 over RT, if we write here 1 over RT, now the first expression is going to be VdP. Now, if you have to integrate both sides, integrating the left side, I'll explain in a short while, is simpler. But on the other side, if you have to integrate it, volume cannot be written explicitly in terms of pressure and temperature, and that makes it very difficult. Also, one thing here, these equations are at constant temperature. So this integration that will be done will also be done at constant temperature. Okay, but VdP can be written as dPV minus PdV, and V ideal gas can be written as RT by P dP. Now, as you can see, we get opportunity to really simplify this expression and solve it out. So this is going to be equal to dPV by RT minus P over RT dV minus RT and RT gets cancelled off, and we are only left now with d ln of P. Simplifying, it's just simplifying out now. Now we integrate the LHS, that is going to be d ln of phi. The lower limit is going to be the state or the gas at pressure and temperature where it's an ideal gas. So we only integrate it from an ideal gas state to a real gas state. Okay, the gas, if it were behaving as an ideal gas at pressure 800 kilopascals and temperature 600 Kelvin, what is the fugacity? That's the lower limit. 2. The fugacity if it were behaving as an real gas at pressure 800 kilopascal and temperature 600 Kelvin. Okay, so the fugacity obviously at the lower limit would be 1. That is because it's an ideal gas. This has already been discussed. For an ideal gas, the fugacity is 1. For a real gas, the fugacity is phi. So we get ln phi. Now this gives us a starting idea for solving it on the RHS. In the RHS, we have dPV by RT is the first term. This can be written as dZ. Now from the state where it's an ideal gas, so for ideal gas Z is equal to 1, to the state where it's a real gas, so Z is equal to Z. And therefore the first integral just becomes Z minus 1. The second integral P over RT, let's leave it at that, dV, where the lower limit is going to be the volume of the gas if it were behaving at ideal gas at pressure 800 kilopascals and temperature 600 Kelvin, to the volume of the gas if it was a real gas, in this case a van der Waals gas at 800 kilopascals and 600 Kelvin. Simple. Minus integral. Now the lower limit of the pressure is also 800 and the upper limit is also 800. So the last term is going to be 0. That is it. So we are only left with these two terms. Pretty simple. That makes calculations all the more simple. So we have ln phi. Don't go about integrating it. Z minus 1 plus, not plus, minus, minus integral. Now replace pressure in terms of volume for a van der Waals gas. So we are going to get 1 over V minus B minus A over RT by V square dV, right? So what do we need to solve? We need V ideal gas, we need V, we need Z, we need A, and we need B. Okay, so let's start the calculation one by one and let's tabulate it so that we don't have difficulty in referring back to it when we want it. So that's going to be the value of A, that's going to be the value of B, that's going to be value of V ideal gas, that's going to be the value of V, and that's going to be the value of Z. So this is V ideal gas, this is B, and this is A, right? So let's calculate these values one by one now. So the value of A is going to be 27 into 8.314 into 600, not 600, 507.4. That's the critical temperature, right? The whole square divided by 64 into the critical pressure, that is 2969. So that's 2528.68 2528.6839. Now let's calculate the value of B. The value of B is 1 into 8.314 into 507.4 divided by 2969. That is okay, and we have to divide this further by 8. So it is 0.1776. So that's 0.1776. So 0.1776. Now we need the V ideal gas. So V ideal gas simply is 8.314 into 600 kelvins divided by 800 kilopascals, and that's 6.2355 meter cube. So 6.2355 meter cube per K mole. Meter cube per K mole, and this is kilopascal meter raised to 6 by K mole square. And now we need to calculate the value of V. So to calculate the value of V, let's write the van der Waals equation in numerical terms and put it in the calculator. So in numerical terms, the van der Waals equation can be written here very simply as 800 is equal to RT. So RT is going to be 8.314 into 600. That's 4988. 4988.4 V minus 0.1776 minus A, 2528.68 divided by V square. Now let's solve this on the calculator. So let's do it. 800 is equal to 4988.4 divided by alpha x minus 0.1776 minus 2528.68 divided by alpha x square. So we have put the equation. Now shift, solve. Now let us give the initial value, which is the ideal gas value. So that's somewhere around 6.23. We need not give a perfect value. We have to give a starting value. So that's 6.23. We know that for sure. And let's press is equal to. So that gives us a value 5.8928. 5.8928. So that's 5.8928 meter cube per K mole. Now the only thing that remains is the value of Z. 0.314. No, that's not 8.314. That's 8.314 on the denominator. So 8.314 into 600, 800, that is the pressure, multiplied by the volume, that is 5.8928. And this is going to be equal to 800 into 5.8928 divided by 8.314 into 600. And that's 0.9450. So that's 0.9450. Now let's rub all this out because we need to do our calculations. So let's get ahead with our calculations. So now what we are going to do is we are going to do a final calculation, that is ln phi is equal to z minus 1, that is 0.9450 minus 1. The second term is minus integral. We have all that we require for the integral, so let's do it. The lower limit is 6.2355 and the upper limit is 5.8928 and it is 1 over v minus 0.1776 minus divided by v square. Now let's make one whole value of this, that is a by rt. Okay, it gets easier to calculate. So a is 2528.68 divided by 8.314 into 600, right? So we have 0.5091, 0.5069, 0.5069. So that's 0.5069. 69. Excellent. We are just one step close to the final answer. We just need to integrate this off. Now let us really ask the calculator to do the number crunching. So that's 0.9450 minus 1 minus integral, start and end the bracket because we have two terms. The first term is a fraction, so 1 divided by alpha x. Okay, so 1 divided by alpha x minus 0.1776 minus the second fraction 0.5069 divided by v square. So that's alpha x square. Now we need to put the limits. 6.2355, 5.8928. That is it. Minus 1.4937. So ln phi is equal to minus 1.4937 into 10 raised to minus 3. Okay. So now let's see what exactly is phi. So let's once again have a look at it. Minus 1.4937 into 10 raised to minus 3. Okay, so your phi is now going to be equal to shift e raised to x minus 1.4937 minus 3. And that's 0.9985 and that is the answer. Phi is equal to 0.9985. Yes, that is the right answer, 0.9985.